Alright, today we look at section 10.4, polar coordinates and polar graphs. This may be something new to you, and so we're going to spend a little time going over it at the beginning, and then tomorrow we'll look at the calculus parts of it, or the next day we'll look at the calculus parts. So first, what is a polar coordinate system? Rewrite rectangular coordinates and equations in polar form, vice versa. Sketch the graph of an equation given a polar form. We'll do that part today. The next lesson you'll see find the slope of a tangent line to a polar graph and looking at several different types of special polar graphs. First, to form the polar coordinate system in the plane, fix a point O called the pole or origin and construct from O an initial ray called the polar axis, and this is horizontal as shown below. If we were to put this on top of the xy coordinate plane, this would be the x-axis, and this would be the origin, 0, 0. Okay, this r that you see right here is called the directed distance, and so we have a point up here called r theta, because that distance has been rotated through this angle, theta, from the polar axis. So you can see here, r is positive, theta is positive as well. It's going in this direction. It's very conceivable that r could be a negative number, which means we would actually go this way from that point, even though the angle was there. Or if theta was negative and r was positive, that the angle would be down this way and r would still go out that way. Okay, so keep that in mind. Each point P in the plane can be assigned polar coordinates r theta. Instead of xy now, we use r theta as follows. R is the directed distance, as I said, from the origin to some point P, and theta is the directed angle counterclockwise from the polar axis. And you can see a couple examples right here. First, we've got the point 2 pi over 3, and oftentimes we use concentric circles here. When we're graphing in polar coordinate form, it's much simpler, easy to see. And then we've got our angle measures from 0 to 2 pi going counterclockwise. So here you can see the point 2 pi over 3. The next one is 3 negative pi over 6. So I, in essence, have gone out 3 units and then down negative pi over 6 units. Okay, and finally the third one here, you've got 3 negative 11 pi over 6. So in this case, and depends how you want to do it, you might say, well, I'm going to start here. I'm going to actually do negative 11 pi over, excuse me, I don't believe that's negative 11 pi over 6. I think that's 11 pi over 6. So not quite sure what we've got going here, because that one can't be positive and the other negative. They're both positive, they're supposed to be, so put a little plus sign in there to make me feel better. Alright, thank you. Okay, so that would be the point, and you can either go out 3 units or around 11 pi over 6 units. I think they just got a little confused with what they were doing before. Notice in the system, it's easy to locate points with respect to the grid of concentric circles using, we call these radial lines. It means they start out from the pole and go out like a radius. So that's what a radial line is. With rectangular coordinates, each xy has a unique representation. Not true at all with polar coordinates. In fact, I can have an infinite number of descriptions for the exact same point. So if I have a point r theta, r 2 pi plus theta represents the exact same point. And if we kind of, not good. We kind of took a look at that and said, well, what does that mean? So I've got, and I'm used to drawing the xy axis, but this is my pole right here. And so if I said I'm going to go out, let's say this is pi over 4, so this is the point, let's say 3 pi over 4. Alright, and that's a straight line, of course. Ooh, not making it any better there. You get the idea. So I went pi over 4 units and I went out 3 units. Or I went out 3 units and then up pi over 4, either way. And imagine now if I went out 3 units, and instead of just going pi over 4, I went pi over 4 plus another 2 pi. Well, it'd land me in the exact same spot. And so we have basically an infinite number of ways to describe any given point. Also, because r is a directed distance, the coordinate r theta and negative r theta plus pi represent the same point. So here in point, let's say r is 3 and theta is pi over 4. How about this time I said, you know what? Let's let r be a negative number. Okay, so I'm going to go, what I'm going to do then is say, I'm going to add pi units to this. So I'm going to say, well, that would put me at, that's pi over 4, so now I'm looking at 5 pi over 4. So that angle would be down here. Let me see if I can change colors. So that angle would now be down. Oh, not good at all. Let's see. That angle would be down here. Pi over 4, 5 pi over 4. And if I was going in a positive direction, it would be here. But if it's a negative 3, okay, instead of going in the positive direction, following that out, I'm going to go in the negative direction. So this point is also negative 3, 5 pi over 4. That takes a little bit of getting used to, so try to wrap your brain around that a little bit. Okay, and so you see these two examples. And n is any integer, and it's just talking about how many times we're going around, basically, all the way around. So keep that in mind. All right. Well, we want to do some coordinate conversion. We're used to things in xy coordinate planes, so that's kind of where we live. But let's go ahead and consider how would I change from one to the other. This is a point, right? If that's a radial line, if you would. This point xy lies on a circle of radius r, and it follows that r squared equals x squared plus y squared using Pythagorean theorem. Moreover, for r greater than 0, the definitions of the trig functions imply that the tangent, so the tangent of theta, is equal to the opposite over adjacent, y over x. And you see that right here. Cosine of theta is the adjacent over the hypotenuse, and the sine is the opposite over the hypotenuse. R is less than 0. You can show the same relationship holds. It's not as intuitive for us. So we simply look at that in this picture right here. But we're going to use these three quite a bit. And you'll see them in just a sec. So the polar coordinates, r theta of a point, are related to the rectangular coordinates. We just solve for x. X is equal to r cosine theta, y is equal to r sine theta, and the tangent of theta is y over x. We also know that r squared equals x squared plus y squared. So these pieces put together make our problem pretty simple. So we've got the point r theta, which is equal to 2 pi in this case. What is it in rectangular coordinate form? Well, the x coordinate is equal to r cosine theta, 2 cosine pi. And the cosine of pi, everyone, is, of course, negative 1. So we would say, let me erase that. We would say here that x equals negative 2. What's my y coordinate for that point? Y is equal to 2 sine pi. Of course, the sine of pi is 0, so y is equal to 0. So my coordinates, my xy here, would be the point negative 2, 0. And maybe if you drew it out, you could convince yourself that that was true. Go ahead and try part B on your own. I think you can do that one. It's not quite as easy, but I think you'll be able to come up with this. Just a refresher on your trig. Let's take a peek at this. How do I graph polar equations? The first one, if I know what r is, well, r represents the length of that line, right? Or from the pole out. it's always 2, if it's always 2, no matter what direction I'm going, so if I kind of just drew that again, oops, I always go to the XY coordinates. But if r was always 2, whether it went there, or there, or there, or here, you could start to see that, hey, I think that's probably a circle. And so that's what it is. It's a circle with radius 2. And it's going to take me longer to write it than it's worth, so that's a circle with radius 2. Here, if I know what theta is, but I don't know anything about r, okay, so I draw another, this time I'll try to draw it right. Here's my pole. Right here, here's my polar axis. If I know that theta equals pi over 3, which is about here, anywhere along here, theta is pi over 3, as well as anywhere down here. Right? So that is simply a line that passes through. And we've got the point 0, 0 on there, of course. And what's another point that would go through there? Well, if I know theta is pi over 3, we could consider any other point. So let's go back and say, well, x is equal to r cosine theta. In this case, the cosine of pi over 3 is, everybody, cosine of pi over 3 is 1/2. The sine is equal to square root of 3 over 2. Okay, so it's a line that's going to pass through those. Okay, and finally, that's when we're going to look at r equals secant theta. Well, secant, if you remember, is 1 over cosine. All right. Well, that doesn't seem to help us much. But hey, you know what? What if I multiplied both sides by cosine theta? What do I get? R cosine theta equals 1. Hey, r cosine theta is x, so I just say x equals 1. That is a vertical line. So in the midst of all the concentric circles and everything that we looked at, I'm just going to kick back here just a minute. Oh, where is it? Right here. We could say, hey, that's a vertical line. It's just going to go right through here. So that would be the graph. I'm sorry for jumping around, but that would be the graph of that one. It's a vertical line. X equals 1. X is always 1. Superimposed onto that graph. And, oh, you can see it right here if I'd known my lesson well enough. So you can see that's happening right here. Here's that vertical line. All right, and I think that's where we're going to stop for this one.